All right, two objects collide and stick together. Let me say a couple of things about collision. So first, momentum is always conserved in collisions. Total energy is always conserved. Total, watch the word here, kinetic energy is only conserved in elastic collisions. And they'll actually tell you that they're elastic. When objects hit and stick, not elastic. So what's going to happen is we can right away rule out choices B and C because momentum is always conserved. We know that it's not an elastic collision by the definition because when they hit and stick, not elastic. So that leaves us with choice D. We actually do lose a little bit of kinetic energy to sound and to heat, friction, whatever you want to call it. But the total momentum is conserved and therefore remains unchanged. All right, number 12, gravitational field strength. Let's remember that G is 10 newtons per kilogram, and this is also equivalent to 10 meters per second squared. And that's how we get choice B. Then we have a ball thrown upwards and then it comes back down. Let's be clear. I want to be super clear on this. When there is no air resistance, okay, acceleration always points down and is equal to G, even at the top when it stops for a split second. So here's what this means. Going up, I get it. The velocity vector, sure, it'll point up like this. Whoops. One more time. So again, as it goes upwards, the velocity vector points like this. As it goes downwards, the velocity vector points like this. But let's be clear, in both situations, going up or down, the acceleration vector is G, and it always points straight down. So at first, as it's going up, it's first in the opposite direction, and then it goes in the same direction. So the answer to 13 is C. All right, for 14, we want to know what's the velocity time graph that represents the motion, and I want to kind of overkill this one. So at first, we're at rest, then we go faster and faster, and our speed levels off, which is exactly what choice A is. Let's take this a little bit further. Okay, an acceleration graph in this situation would look like this. The correct acceleration graph would be you have a steady acceleration to begin with, and then it dies off. So this is how your acceleration graph would look. And the position versus time graph. At first, you start at rest, and then you go and gain position. You have this nice parabolic curve representing the fact that as each second goes by, you cover more distance. And then you hit the ground, the level part of the ground, and you continue at a steady pace in a straight line. So this part is a line, and this part is a parabola, just to keep it safe. Now, this goes back to number 15, goes back to exactly what we talked about in number 13. When there's no air resistance, acceleration always points down or is equal to G even at the top when it stops for a split second. Force at the top. A ball is thrown vertically upwards at the top of its path. What forces, if any, act on the ball? Only a downward force. And this downward force is gravity or its weight. The same 100% totally identical idea. Okay, the force of gravity or the force of its weight. 16, let's be clear. So marker 1 is half of the distance, right? Now, when do we gain half of our speed? Let's be clear. So from here to here, we go 70 kilometers per hour. Let me explain why I say it's before marker 1. Because I have some time here and some time here, and these two times are equal for the travel. So my average speed from here to here is on average slower, and here on average it's faster. So for the second time half of the trip, I'm actually traveling faster than for the first time half of the trip. So if I time it, it turns out it's going to take me longer to accelerate from 0 to 70. It's going to take me more distance to go from, because I'm going from 0 to 70, I'm traveling on average slower, so I'm going to cover less distance in the same amount of time as going from 70 to 140 because I'm on average faster for that second part. So it turns out the answer is A, before marker 1 is when I'm going to actually achieve that speed. It's a really good trick question. Now, the velocity versus time graph. Oh, I can tell you right now, whenever I see something like this, I have a feeling it's going to be an area question. So I'm just going to say the area of the truck is greater than the area of the car. And what that means is that the distance of the truck is going to be bigger than the distance of the car. So I'm going to circle C tentatively. Sorry, D. But let's actually read the question. So we've got velocity versus time graphs, and we're told that time t, which one has traveled further? So choice D is in fact correct for number 17. And for number 18, the acceleration while towing a van. This is where we're going to need to do a bit of comparison, so let's be clear on this. So first, let's do a before and an after. Before, I've got the force just on the car, and that equals mass of the car times A. Afterwards, what's going to happen? I'm going to have force of the car equals 3 times mass of the car times this new acceleration that I'm solving for. Let me do a little comparison. FC divided by MC is A, and I'm going to call this A old. So that's the old acceleration. What does the new acceleration equal to? FC equals 3 MC times A new. Again, it's because I've got 1 MC here and 2 MC here for the truck. Looks more like a hearse. So when we solve, we're going to get that A new is FC over 3 MC. So when I compare, A new is 1/3 of A old. Okay. Now, these two balls fall. Let's be clear. In the absence of air resistance, everything's going to hit the ground at the same time. So we can rule out A and B. But why? C is really tempting to pick because it's the easiest, but it actually turns out D is correct. Let's be clear. Gravitational forces in P and Q are equal. Remember, you can replace the word gravitational forces with weight. So if this is iron and this is wood, do you really think they weigh the same? Of course not. Here's what it is. You have mg here for the iron and little mg for the wood. So you have force on the iron and force on the wood. And let's be clear, when we divide by m, we end up getting the same acceleration for each, which is good old gravitational acceleration, 10 meters per second squared. The way we write that in English is the ratio of gravitational force to mass is the same for P and Q. In other words, this fraction here equals that fraction there. And then number 20. To be clear, the equilibrium point is the midpoint of the motion. This is where F net is 0. This is where Kx is actually going to equal mg. And the net force is 100 equal where kx is the spring force and mg is the weight, and that's exactly where they balance to give me no net force. So that is questions 11 through 20.